So let's focus in depth right now, zoom in and focus on physical methods of control. First up, we have heat. There are two kinds of heat. We have both moist heat and dry heat. Now, just an elevated temperature, just having a hot temperature or a lot of heat is going to be microbicidal, so it's going to kill microbes. Lower temps are going to be considered microbial static. So think of a freezing temperature, so to speak. Those are microbial static temperatures. Or if we have a slightly elevated temperature, not enough to kill the microbe, but enough to make the environment so unfavorable that the microbe cannot reproduce. Our moist heats, generally speaking, are going to be hot water, boiling baths, or steams, and these can vary from 60 degrees Celsius to 135 degrees Celsius, depending on the pressure of the system. If we have open air at atmospheric pressure, or if we're boiling at atmospheric pressure, or if we are heating in a pressurized tank. Dry heat is typically going to go from 160 degrees Celsius up to thousands of degrees Celsius. It's hard to find an upper limit for dry heat. Usually it's going to be a dry oven or a warm air oven that will go through this process for us. So let's focus on the moist heat first. Moist heat will work at lower temperatures. It's going to be a little bit more effective at lower temperatures and at shorter exposure times than dry heat. The microbicidal effect is that we have coagulation and denaturation of proteins. So when you cook something at a lower moist temperature, you are going to cause the proteins within that microorganism to denature so that the metabolic pathways within that microorganism can no longer be maintained. Dry heats work on a different principle. Instead of denaturing the proteins and coagulating the proteins, we want to dehydrate the cell. By removing all of the water necessary for the metabolic functions, we are going to cause that cell to not have a universal solvent to carry out its chemical reactions in. This dehydration process is also going to denature the proteins. Some proteins are going to have increased stabilities, so they're going to be extra stable proteins. These are proteins generally that are going to be found in our extremophiles, like Thermus aquaticus. And these proteins are going to need extra high temperatures to kill or denature. So this is where dry heat can come in handy. At very, very high temperatures, we don't just dehydrate the cell, we burn it. So we oxidize everything. We burn the cells to ashes, and that absolutely will destroy the cell. So we can look at our different temperatures and our different kinds of heats in this table. Moist heats operate at lower temperatures and lower time periods to achieve sterilization. Dry heats operate at higher temperatures and longer time periods to achieve sterilization. How long it takes something to die and the temperature that it dies also is influenced by what we're trying to kill. Bacterial endospores, generally speaking, are going to be tougher to kill than our vegetative cells. Our bacterial endospores have a great resistance to death. Destroying a bacterial endospore requires a temperature above the boiling point of water, above 100 degrees Celsius. So if we're using those moist heats, we need to use a moist heat that is under pressure in an autoclave or a pressure cooker. Depending on the specific endospore you're looking at, the resistance of that endospore to dying or death is going to vary from organism to organism and species to species. Our vegetative cells are going to be much easier to kill. Our vegetative cells have a much higher sensitivity to heat compared to our bacterial endospores. Their death temps can be as little as 50 degrees Celsius for 3 minutes or 60 degrees Celsius for 60 minutes, depending on the kind of organism we're working with. E. coli, for example, would die at 50 degrees Celsius at 3 minutes, but Thermus aquaticus would take 60 degrees Celsius for 60 minutes. It would take that much warmer temperature. Our vegetative cells also have our spore formers have the same susceptibility to heat as vegetative cells of non-spore formers. So in other words, it does not matter if that species is capable of producing a bacterial endospore. If that species is in the vegetative state, if we're working with a cell that's actively growing, that cell is going to be very easy to kill regardless if the microorganism has the ability to make a spore. The pathogens that we are going to want to destroy, generally speaking, have the same susceptibility heat sources as the non-pathogenic microorganisms that we kill along with the pathogenic microorganisms. So if we look at our fungi or protozoa or worms, all these different kinds of pathogens that can make us sick, they're all going to have a similar sensitivity to heat. Our viruses are more resistant to heat than many microorganisms. This tolerance for heat for viruses, it stems from the fact that they're simpler. There is not as much in a virus that can go wrong, so it's harder to take a active virus and deactivate it and make it so that it's no longer capable of infecting the cell. The amount of time it takes to kill a microorganism is known as the thermal death time. And this is the minimum amount of time. It's the shortest amount of time it takes to kill a microbe. Thermal death time varies from temperature to temperature. The thermal death time at 10,000 degrees Celsius is going to be a heck of a lot shorter than the thermal death time at 50 degrees Celsius. The thermal death point is different from the thermal death time in that the thermal death point is the temperature required to kill all the microbes in a sample at within a 10-minute period. So our thermal death point, generally speaking, is going to be much easier to work with. It's a more useful measurement because most people have 10 minutes. Most people can wait 10 minutes to kill the microbes in a sample. We just need to know what temperature to heat the sample up to in order to kill the microbes within that 10-minute period. If we look at perishable substances, such as a beverage, for example, like milk or beer, we can heat treat that substance to render it free of agents that may potentially spoil it or cause it to go bad. And this can be done without necessarily affecting the speed or cost of processing the beverage. So let's look at some moist heat methods for decontaminating or disinfecting something. We can boil it. Boiling just water on an open pot and an open stove is very useful for disinfecting something in your home. This is great if you need to disinfect water for babies or if you need to disinfect some clothing from somebody that's sick. Throw it in some boiling water. This is great for almost all the situations you'll encounter in your home. If you're processing beverages and you want those beverages to not spoil within a short period of time, generally speaking, you heat up that beverage, and the process of heating up the beverage is going to kill many of the vegetative microorganisms within that beverage. This is known as pasteurization, named after yours truly, Louis Pasteur. Pasteurization is done with beverages that start out with high concentrations of microorganisms or have the potential to pick up high concentrations of microorganisms. Wine, milk, beer, and a wide variety of other beverages are commonly pasteurized. Simple pasteurization does not kill everything. For example, if we take milk that's been freshly pasteurized, it still contains thousands of microbes per milliliter of freshly pasteurized milk. What does this mean? This means that even if the milk has been pasteurized, it will still spoil. It eventually will go bad. It takes a while. It takes longer than if you did not pasteurize it, but it still does go bad eventually. There is a new kid on the block. This is relatively recent. It's ultra pasteurization. This is super duper high temps for very short periods of time to sterilize a liquid or disinfect the liquid. And milk and other beverages that have gone through ultra pasteurization, generally speaking, are going to be shelf safe for a period of months. If you go to a grocery store, you can find regularly pasteurized milk in the milk cooler. That milk needs to be chilled to inhibit microbial growth. But ultra pasteurized milk can be put in a box and stored on a shelf at room temperature. So, like my wife and I in particular, we have some soy milk and some almond milk that's been ultra pasteurized that we keep in our cupboards just in case we have company come over that have special dietary restrictions so that we can be accommodating for them. And then once every 3 months, I pull it off the shelf and I have it with my cereal. It works out pretty nicely. We can also have high pressure moist heat. This is going to be pressure cooking or autoclaving. With this high pressure moist heat, we are going to have a pressure chamber that can be pressurized higher than atmospheric pressure. Generally speaking, 15 psi is the highest that we go. And then we are going to pump high pressure steam and high temperature steam. Because of this high pressure environment, we are able to achieve a temperature greater than 100 degrees Celsius, which makes it easier to sterilize the substance. High pressure steaming is a great way to disinfect to sterilize something. Use in an autoclave will sterilize. It will kill all vegetative cells and all bacterial endospores. These methods are for disinfecting. They do not destroy bacterial endospores. Autoclaving does destroy bacterial endospores. We can also have dry heat methods. Incineration, running it through an open flame, will absolutely destroy all bacterial endospores. Those Bunsen burners can get really hot. They can approach 1900 degrees Celsius, so that is quite toasty, and it burns the living daylights out of everything. So if you're working with a relatively small piece of metal or glass, running it through an open flame is a great way to sterilize it. It works very well. Or if you have a piece of organic matter, and you are not concerned with keeping the organism alive. Let's say you have an animal carcass that's been contaminated with a pathogen. You can just burn the carcass. We also have hot air ovens. Hot air ovens work great if you need for sterilizing large, bulky items that may not necessarily be safe to run through a flame. So we could take high temperature plastics, for example, and these large, bulky or wood, for example, is another example of something that can be sterilized in a hot air oven. You need to be careful, though, particularly if you have a carbon-containing compound, that you don't scorch or brown that carbon-containing compound in the hot air oven. This hot air oven will take a longer period of time than incineration for sterilization because it works with much lower temperatures. Let's talk about cold. We spent a lot of time talking about hot stuff. Let's talk about some cold methods for inhibiting microbial growth. The nice benefit of cold temperatures is that it slows the growth of microbes. Cold retards the activities of microbes in most situations, or it slows the activities. In most situations, cold does not kill. Cold makes dormant. Cold doesn't make death. Most microbes are not going to be adversely affected by gradual cooling or long-term refrigeration or deep freezing. In other words, putting something in your refrigerator or putting something in your freezer does not disinfect it. I remember I was a freshman in college, and someone was trying to convince me that if I put my sandals in my freezer in my dorm room, I would kill all the bacteria on them, and then my sandals would not smell as bad. Believe it or not, it didn't work. My sandals still smell terrible afterwards. Now, when we are looking at really cold temperatures, anything from -70 to -35 to 135 degrees Celsius, we can preserve cultures of bacteria and viruses for extremely long periods of times. Usually these are going to be stored in some kind of a glycol solution so that we can minimize the amount of damage from ice crystals. Desiccation is drying. Generally speaking, we'll take the cells and expose them at a general room temperature and gradually dehydrate them. Some microbes are going to be killed by desiccation. Others don't necessarily have any effect from desiccation. So desiccation is just a drying out or dehydrating of the microbe at room temperature. And then we have lyophilization, aka freeze drying. In this method, we're going to freeze and dry out the microorganisms. This is a way of preserving microorganisms for a long period of time. If we remove the water, we remove the ability for ice crystals to form, and by freezing, we are going to allow them to remain dormant for a very long period of time. If we have a pure culture, we'll flash freeze them, typically in liquid nitrogen, and then expose them to a vacuum that removes the water. Liquid nitrogen is great because that flash freezing from the liquid nitrogen causes there to be incredibly tiny and small ice crystals. And then by exposing this flash frozen sample to a vacuum pump, we suck off the water through sublimation and then reduce the ability of larger ice crystals to form later on in the process. Another method of sterilizing or disinfecting our cultures and microbes is going to be radiation. Our three primary sources of radiation are gamma rays, X-rays, and ultraviolet radiation. These are all going to be on the electromagnetic spectrum, just like visible light is. What is radiation? Radiation, simply put, is just any kind of energy emitted from an atomic activator, atoms interacting with each other. Radiation can move at very high speeds. It moves at the speed of light. And it can go through matter, and it can go through vacuum in space. So here's the electromagnetic spectrum. We have visible light as that narrow bandwidth right here from approximately 400 to 750 nanometers. Radio waves are at the lower end of energy spectrum. Radio waves and microwaves are low energy, high, long wavelength waves. Gamma rays, X-rays, and ultraviolet radiation are short wavelength, high energy forms of electromagnetic radiation. Gamma rays being on the highest end of the spectrum. So we can use ionizing radiation, gamma rays and X-rays. Those are ionizing radiations, and they are capable of killing bacterial endospores. Ionizing radiation, such as gamma rays, have been used for a while to sterilize food products. I know many individuals become very concerned about ionizing radiation being exposed to their food, but it's actually been found that there are very few harmful effects. Ionizing radiation, generally speaking, is going to reduce the amount of vitamin B1 or thiamine within the food sample that's being ionized with gamma rays, but the reduction in vitamin B1 is negligible and has not been linked to any ill effects. This ionizing radiation, or use of gamma rays to sterilize food, is so effective and so safe that it's actually used to sterilize all of the food that NASA sends into outer space. Because if you send food into outer space, it's really, really expensive to get it into orbit, and you really, really, really do not want it to spoil and go bad. Another example of the use of gamma rays is U.S. postage mail. After the anthrax attacks after 9/11, is now ionized with gamma rays, depending which federal building it's going to. We can also use non-ionizing radiation, aka ultraviolet light, UV radiation. This UV ray will form thymine dimers. UV rays are, generally speaking, going to be used to disinfect the air. If you have a high-end HVAC system in your home, you may have an ultraviolet lamp present in your heat exchanger to help minimize microbial growth, present where you cool your air, and to help sterilize the air before it's pumped through your house. Here we have a normal segment of DNA, and we have two thymines right next to each other. If a photon of ultraviolet light hits those two thymines, it will form a thymine dimer. Covalent chemical bonds, a double covalent bond specifically, will form between those two thymines, making a thymine dimer, and now the thymines are no longer linked to the adenines. If this mistake or mutation in the DNA is not fixed, and we go through a round of DNA replication, this becomes a permanent mutation in the microbe. This mutation is the exact mutation that I use to sterilize my goggles in my laboratory setting. I have an ultraviolet lamp in my goggle cabinet, and I use ultraviolet light to blast my bacteria with non-ionizing radiation that causes the DNA to get destroyed. This is coincidentally the same kind of light that's in a tanning booth, and it's the same kind of light that we get hit from by the sun, and it's a reason why we should wear sunscreen. Up next for our methods of physical control, we have filtration. Filtration is remarkably straightforward, remarkably simple. You just need to remove the microbe to disinfect the liquid or sterilize the liquid. And if you pull all the microbes out of the liquid, then the liquid needs to be sterilized by definition. Fluids are easier to sterilize than air because we can force them through finer filters. So if we filter this fluid with a filter with openings that are large enough for the fluid to go through but too small for the microbes, we are going to disinfect or sterilize our fluids. Sometimes there is going to be a thin membrane of cellulose acetate, polycarbonate, and plastics. And in those situations, we can very carefully control the pore sizes. Other things that we can use to filter our liquids include charcoal, diatomaceous earth, or earth that basically looks like glorified sand, or unglazed porcelain are also used as filters. My older brother, for a while, was working on a project to come up with low-cost methods to disinfect water in developing countries, and his team came up with the method of just filtering the water through a terracotta pot. That terracotta pot essentially was a form of porcelain, and you could let the water seep through the terracotta pot and become effectively sterilized or safe for human consumption through that process. Pore sizes can be controlled on your filtration device to allow viruses to be trapped or to even allow large proteins to be trapped, but still allow for the liquid medium to travel through. So filtering of liquids is a very effective method. However, it's a very slow method. We will typically take liquids that cannot withstand heat and filter them to disinfect them. So if we look at blood serum, blood products, vaccines, IVs, enzymes, and growth media, things that will be destroyed by high heat, we will sterilize them through filtration. It's quicker and easier to use high heat. So that's going to be the preferred method. But if we are in a situation where we can't use that high heat, we'll opt towards filtration. Filtration has been found to be an alternative method for sterilizing milk and beer without altering the flavor like pasteurization does. For water purification, filtering is a very essential step. Most municipalities go through several rounds of filtering before pumping water to your homes. It's also very important to remove soluble molecules or toxins that can cause diseases. For home water filtration systems, typically that's going to occur in the charcoal filter stage. We can also have high efficiency air particles or HEPA filters that are used in hospital rooms and sterile rooms. Those remove most microbes from the air, and if we take a high efficiency HEPA filter and pair it with an ultraviolet lamp, we can have nearly sterile air. Here's a good example of a typical filtration method. We have our filtration membrane right here with pores. These are very, very tiny pores. If we look here, we can see the pores are smaller than 2 microns. So this is a 2 micron white bar on the side. So these pores are measured probably in the hundreds of nanometers scale. So they're itty bitty tiny little pores, way too small for the bacteria to travel through. It also takes a while for the liquid to get through this filtration device, so we speed up the process by exposing the underside to vacuum pressure to cause the liquid to get sucked through the pore at accelerated rates. And notice that bacteria are on the surface of the pore, they cannot travel through it. Finally, another physical method we have for disinfection is osmotic pressure. What do I mean by osmotic pressure? I mean by changing the concentration of our dissolved solvents. Usually we're going to use salt or sugar if we're working with some kind of a food product. So you can, for example, we can think of beef jerky or jams or jellies. And these create very hypertonic environments. Remember, we have hypertonic, isotonic, hypotonic. In a hypertonic environment, we have a higher concentration of dissolved solutes outside of the cell and a lower concentration inside of the cell, causing water to be removed from the cells. During this process, the bacterium is going to have plasmolysis induced. In other words, the bacterial cell will be shriveled up and die. Pickling, smoking, drying has been used for a very long time to preserve food. Osmotic pressure never can sterilize. It does not destroy endospores. Osmotic pressure will inhibit the growth of active vegetative cells, but it does not sterilize, it does not kill endospores. This is one of the big reasons why you need to worry about botulism poisoning, for example, if you're making homemade pickles, for example, and you don't do a good job of pressure cooking those homemade pickles. So, concept check class, which of the physical control methods would be used to sterilize the following items? An inoculating loop, glassware, vaccines, powders, and oils. You can pause the video and rewind, or you can check your textbook or check your PowerPoint slides. Pause it and find me an answer. 1, 2, 3, 4, 5. For the inoculating loop, you would absolutely run it through a Bunsen burner and use flame incineration to sterilize it. For glassware contaminated with bacteria, you would take that glassware and you would put it in either an autoclave or a dry heat oven. Both would work to sterilize it and decontaminate it. For a vaccine, vaccines, generally speaking, cannot be exposed to high temperatures for extended periods of time, so we are going to go and use ionizing radiations, such as gamma rays, to disinfect and sterilize the vaccines. And then finally, for powders and oils, if it's an oil, we can use pasteurization. If it's a powder, we can use a dry heat oven to sterilize it. If you have any questions about this reading or about the chapter, please post them on the discussion board or shoot me an email. Happy studies!